In this problem, we will calculate the electronic structure and magnetic properties of an important transition metal ion, iron 2+, and iron has atomic number 26. What is the electronic configuration of an iron 2+ ion? Note that the transition metals give up their 4s electrons first before their 3d electrons on ionization. Now, if I write the electronic configuration of iron, which has atomic number 26, this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. And if I have the iron ionized, iron 2+, so now I have 24 electrons. Because it's mentioned here that the 4s electrons are given up first, for iron 2+, I will have 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. So this will be the result because 4s electrons are lost in the ionization process. Let's move on to part B. Use Hans rules to determine the values of total spin, total orbital angular momentum, and total orbital angular momentum quantum numbers in the ground state of an iron 2+ ion. Okay, so we have the outmost partially filled orbital is 3d. So we're going to work on this orbital. So if we have L equals to 0, orbital angular momentum quantum number, those are s orbitals, L equals 1, p orbitals, L equals 2, d orbitals. And what we have is L equals 2. So with that, the magnetic quantum number, m sub L, can take values -2, -1, 0, +1, and +2. So if you consider the d orbitals, we have for each m sub L value -2, -1, 0, +1, and +2, we have 5 subshells. And the way we're going to place these electrons, if you remember Hans rules, the first one is maximize the total spin quantum number. This will be sum over m sub s values for each electron. For the m sub s value for the ith electron, we will sum over all electrons. And when we place these electrons in these orbitals, subshells, in order to maximize s, we have all of them pointing in the same direction, but that makes 5 electrons because we have 6 electrons. We need to put one of them in the downward direction. So this s is going to be then 5 electrons with 1/2 value and one of them with -1/2 value. So it's going to be 2. So we will find that the total spin quantum number is 2. And second Hans rule, um, is basically maximize total orbital angular momentum quantum number, and we can sum over all electrons m sub l values to find this quantum number, and L is going to be, the reason I have put the last electron in the m sub L equals 2 is to maximize L basically, so that I will have -2, -1, 0, 1, 2, and 2. So the answer will be 2. Therefore, the total orbital angular momentum quantum number will be 2. And then Hans' third rule, if the d orbital is more than half full, we have J is equal to the sum of L and S, so it's going to be 2 plus 2, so we will find that J is equal to 4. So the total angular momentum quantum number J will be equal to 4. So we have gone through Hans' rules to determine capital L, capital S, and capital J values. In part C, we're going to calculate the Lambda G factor. So the Lambda G factor is equal to 1 plus J plus 1 plus S plus 1 minus L plus 1 divided by 2J plus 1, and this is going to be equal to then 1 plus 4 times 5, 2 times 3, 2 times 3, and 2 times 4 times 5. So this will be equal to, because these two will cancel, 20 divided by 40, 1 plus 1 over 2. So we will find that the Lambda G factor is 1.5. And let's move on to part D. Calculate the total magnetic moment, G square root Jj plus 1, and magnetic moment along the field direction. Compare your result with your answer to exercise 1.3b. Okay, so the total magnetic moment, G square root J plus 1 Bohr magneton, will be equal to 1.5 square root 4 times 5 Bohr magneton. So M total, we will find 6.7 Bohr magneton. And then we need the projection onto the field axis. So the M is equal to minus G M sub J Bohr magneton, and M sub J values, because J is equal to 4, M sub J values are minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. These are the possible values. So for M, we can have M sub J times G, so it's going to give us for 4 times 1.5 is 6, so 6 Bohr magneton. So we can have values as minus 6 Bohr magneton, minus 4.5 Bohr magneton, minus 3 Bohr magneton, minus 1.5 Bohr magneton, 0, 1.5 Bohr magneton, 3 Bohr magneton, 4.5 Bohr magneton, and 6 Bohr magneton. So this will be, these are the possible values that we can obtain for M. This is along the field axis. Okay, so we want to compare this to exercise 1.3b. So let's go back to exercise 1.3b. So we found that for a classical electron that's moving in a circular orbit of radius 1 angstrom with angular momentum h bar joule seconds, the magnetic dipole moment of the electron that we find was basically equal to a Bohr magneton. So basically we have an answer that is comparable to this classical result where we use where we find the answer to be a Bohr magneton. Okay, so the comparison gives us the following result. The classical result was that the magnetic moment of an electron due purely to orbital motion. So we were only considering orbital angular momentum. Orbital motion was of the order of a Bohr magneton. And we find that our result has the same order of magnitude. Okay, so that's the comparison. The same order of magnitude is what we find here. So part E of the problem, try calculating the total magnetic moment using the value of S, assuming L is equal to 0, so that J is equal to S. In fact, the measured value is 5.4. So we're going to calculate total magnetic moment, and this time J is equal to S. So if we take S value, S equals 2, but L equals to 0, J is equal to 2, the lambda factor becomes, if you go back here, if you have L is equal to 0 and J is equal to S, you will have 2SS plus 1 divided by 2SS plus 1 plus 1 as the G lambda factor. So G will be 2. So this is the spin only lambda factor. G is equal to 2. Then we would have, for the total magnetic moment for the iron 2 plus ion, basically it's going to be G square root JJ plus 1 Bohr magneton, G square root JJ plus 1 Bohr magneton. So this will be equal to 2 square root 2 times 3 Bohr magneton, and we find M total to be 4.9 Bohr magneton. So it's quite different. What we found in part D was 6.7. Here it's actually 4.9. The measured value is 5.4 Bohr magneton. So J equals S gives a closer value to as compared to experimental result. So what is the conclusion? Why is that the case? So it appears that there is a mechanism for the orbital angular momentum contribution to be quenched to some degree. So the lesson we learn is that it appears that the orbital angular momentum is quenched to some degree. So quenched means it doesn't respond the way it's supposed to the magnetic field. It seems to be fixed in position, and as we will find out, it's actually quenched due to the crystal field. The electric field environment basically forces the orbital to be fixed and not responding as much as it should to the change in the external magnetic field. Okay, so we have gone through the exercise of calculating the electronic structure and magnetic properties of iron 2 plus ion. First, we find that its electronic configuration ends with 3d6 because 4s electrons are given. The 3d6 orbitals using Hans rules has L equals to m sub L values minus 2 to 2. So there are 5 subshells. The spin is maximized, S becomes 2. The orbital angular momentum is maximized, L equals 2. And J is equal to L plus S if it's more than half full. If it was less than half full, it would be L minus S, absolute value of L minus S. So it's going to be equal to 4. Then the lambda factor we calculate using both orbital and spin contributions is 1.5. And the total magnetic moment is G square root JJ plus 1 Bohr magneton. It's 6.7 Bohr magneton using both spin and orbital angular momentum contributions. And the values, the possible values of the magnetic moment along the field axis range from -6 to +6 Bohr magnetons, changing in units of 1.5 Bohr magnetons. We find that if we use S equals 2, L equals 0, spin-only contribution, the total magnetic moment becomes 4.9 Bohr magneton, which is closer to the experimental value 5.4 Bohr magneton, which is indicating that the orbital angular momentum contribution is somewhat less than what we thought. It's quenched due to some degree. And the results that we find here are of the order of a Bohr magneton, which agrees with the classical result where we only considered the orbital motion of the electron.